Let's begin by looking at the Grand Canyon. The Grand Canyon is one of the most visual representations of time passing, what geologists call strata. Everyone has seen the images of strata in the American West. There is layer upon layer of different colored sedimentary rocks that are both so beautiful and yet so impressive. When looking into the Grand Canyon, you can't help but to be amazed by the record of the geologic past. John Wesley Powell was a geologist and explorer who rafted down the Colorado River through the Grand Canyon in 1869. During that journey, he took time to try to grasp the big picture of canyon geology, which I quoted a little in the first lecture of this course. Let's read more of what he had to say. I climb up the granite to its summit and go way back over the rust-colored sandstones and the greenish-yellow shales. To the foot of the marble wall, I climb so high that the men and boats are lost in the black depths below, and the dashing river is a rippling brook. And still there is more canyon above than below. All about me are interesting geological records. The book is open, and I can read as I run. A lot of what we are reading in such environments are the layers that geologists call strata. The word strata comes from the Latin word for a bed or cover, something spread or laid out. Geologically, the word strata, which is plural for stratum, refers to layers. Because of the nature of sedimentary processes, the definition is very apt. Geologic layers cover the layers beneath them. Biologists use the word strata to describe layers of tissue or organ structures. In popular writing, sometimes people will mention economic strata to indicate certain levels of income. In cooking, it's a type of layered casserole. A favorite example of breakfast strata is a layer of bread, a layer of eggs, a layer of cheese, and whatever else you want to throw on top. Geologic strata do hold an interesting record of the Earth's history, and the science of stratigraphy is the branch of geology that encompasses that field of study. In fact, stratigraphy and the establishment of stratigraphic principles is what really began the development of geology as a science. Stratigraphy provides the framework within which sedimentary strata can be studied systematically. It's important to remember that stratigraphy really is focused on sedimentary units. Stratigraphy allows the geologist to take the characteristics of the sediments and sedimentary rocks that we talked about in an earlier lecture, sediment grain size and characteristics, color, composition, and sedimentary structures, and then synthesize those characteristics into a regional interpretation of changes in environment and conditions through time. You literally read the rocks. Stratigraphy had an interesting beginning. As you know, the earliest interpretations of geology had trouble reconciling fossils and sediments that clearly resembled things in the ocean, but were found either on mountaintops or miles away from the coast. And then came Niels Stensen, later known as Nicholas Steno. Steno was educated to be a doctor. He was Danish and went to school in Copenhagen. He quickly was recognized as a talented scientist and a keen observer when he was a student. In fact, as a student, he was the first medically trained individual to notice the Stensen duct, a duct in the rear of the mouth that controls salivation. But complications in Denmark resulted in him moving to Tuscany, Italy, to continue his studies and research. Fortuitously, an enormously large shark was caught and saved for scientific analysis. Steno was sent to analyze this monstrosity. In the process of the analysis, Steno recognized that the teeth of the shark resembled fossils frequently found in the area. Those fossils were believed to have been dragon's tongues. Steno recognized them as evidence of sharks that had lived in the past, and he realized that the rocks that contained those fossil shark teeth at one time had been underwater and formed as ocean sediments. he started thinking about sedimentary rocks. Steno's observations created the foundations of stratigraphy. He realized that sedimentary rocks occur as layers or strata, and that the characteristics of an individual stratum reflect the environmental conditions at the time the sediments were deposited. Therefore, change in strata represents some type of change of the environment. He also recognized that all strata were not the same age, and as the word implies, each strata covered the strata below it. But what kind of change causes a change in sediment type? The answer is a lot of things. This is the great joy of stratigraphy. Interpreting the stratigraphic record allows you to interpret environments and how they change through the geologic past. One example is sedimentary rocks that are red. They're frequently called red beds, and there are some that are really distinctive. But does the color actually tell you something about the geology? The answer is yes. In many cases, red beds form as continental sediments, that is, as rivers and alluvial fans. There are several ways the color can be attained: at the time of deposition, as the sediment is buried, and much later in time when it becomes a rock. But the key is having iron in the system, which is altered to ferric oxides. What's interesting is that red beds are more common in certain geologic times. These appear to be times when the atmosphere may be going through some changes and extremely high rates of oxidation are occurring. So the change that caused the deposition of a different color sediment is probably change in the oxygen available in the atmosphere. I always tell my students, when I say Triassic, you say red beds. Triassic red beds are really distinctive rocks in the Connecticut River Valley, in the Black Hills, and in the Four Corners region. But red beds also are common in the Devonian and the Permian periods. The Old Red Sandstone in England and the Permian red beds of Texas are famous examples. So with a little bit of prior knowledge of simply seeing red sedimentary rocks allows you to start homing in on the geologic setting and origin, the age and environment, just by seeing red. Steno did more. In addition to recognizing that changing strata represented changing environments, Steno also recognized several important characteristics of strata based on the mechanics of deposition of sedimentary particles. Steno stated that the sediments that make up a stratigraphic unit will be deposited in all directions, extending until they end abruptly at a basin wall or they pinch out, because you simply run out of sediment to distribute. In other words, if you find sedimentary strata in one place, you can expect to find them in another place. This is called the principle of lateral continuity. This is the most practical principle of stratigraphy. It states that if you find a geologic stratum that has a valuable component, oil, coal, or an economically important rock or mineral, you can expect to find that same stratum nearby. For the beginning geologist, this means that if you find fossils in a sedimentary bed in one place, you should also find similar fossils in the same bed at another place. Take a river cut. In sedimentary units, if you found something interesting in the rocks on one side of the river, look across to the other bank. Are the strata the same? If so, you should find similar features on the other side. The process of matching strata from place to place is called correlation, and correlation is the means that geologists use to map the occurrence of strata over large distances. This concept was critical in driving the Industrial Revolution in England. William Strata Smith was the first professional geologist. He's most famous for making the first geologic map in 1815, a geologic map of England, Wales, and southern Scotland. Many call it the map that changed the world. At the time, 400 copies were printed, but fewer than 40 are still known. The importance of the map was its accuracy. Smith used fossils to correlate important strata. Not only was he mapping coal beds to be used as fuel, but also rock types that could be used for other purposes, constructing canals, building bridges, and for agricultural purposes. It was his work that established the very practical importance of stratigraphy. Let's stick with coal for a while. What's coal? Coal is an organic sediment. It consists of solid bits and pieces of undecayed plant material. Coal is typically concentrated as individual layers, called coal seams, interbedded with other sedimentary rocks. So coal is an example of a geologic strata that formed in a very different environment than the underlying and overlying strata. I can't think of a better example of changing stratigraphy and changing environments than the Carboniferous coal seams and the sedimentary units found above and below them. To preserve coal in thick accumulations in a geologic record, two things have to happen. You need abundant vegetation and you need a place to collect it. Abundant vegetation usually means a warm, moist climate. In the Carboniferous, for example, most of North America was at or near the equator, and the continent was frequently covered by shallow seas. Collecting vegetation to form coal requires a sedimentary basin where large masses of dead vegetation can accumulate. To make a 1-foot layer of coal, you need 10 feet of accumulated vegetation. Coal seams can be up to 90 feet thick. To form that, you need a layer of vegetation that was 900 feet thick. Like any fossil, if that accumulated vegetation is covered relatively quickly by clastic sediments, the organic material won't decay or oxidize. And in time, geologically speaking, you get coal, a classic example of a fossil fuel. So I'll ask you, when you're thinking about changing conditions and the generation of different strata, where would you expect to encounter conditions that, one, have a lot of vegetation, two, have basins where the vegetation will accumulate, and three, have enough sediment to bury it? Before you answer, there's one more thing to know. Whatever those conditions were, they occurred repeatedly. One of the weird things about the Carboniferous of the U.S. is that 30, 40, and up to 100 coal seams are found stacked in stratigraphic layers. The accumulation and burial of these thick layers of vegetation occurred over and over again. How did that happen? It turns out that because of the importance of coal as a fossil fuel, geologists have been studying it for years and years. Coal seams show up in what are called cyclothems. They are called cyclothems because at first glance, they appear to repeat the same geologic strata, including a coal seam, repeatedly. Cyclothems look like this. Their basal stratum was deposited in fresh water, a sand layer probably deposited by a river, a muddy shale or calcareous shale, which is overlain by a freshwater limestone. These fine-grained sediments were deposited in a lake. The next layer is called underclay, a soil which has abundant root casts, evidence of lush forests. Not surprisingly, the coal seams form directly above the underclay. So you have freshwater sediments deposited by rivers and lakes that is overlain by deposits of a coastal forest or a swamp. What happens next is the deposition of sediments in brackish or saltwater environments. Clay and limestone commonly cover the coal seam. Sea level is rising and the vegetation is submerged as the position of the shoreline changes. For the rest of the cyclothem, you have different types of saltwater environments reflecting varying marine conditions. How do you repeat a cyclothem? The sea level lowers and the land surface is uncovered, and rivers and lakes deposit the lower strata, followed by the formation of a coal-bearing swamp. The process repeats over and over again. So you know where that happens, right? It's a river delta. You can imagine it happening in Louisiana or the Florida Everglades today. Rivers meander, bayous form, and vegetation accumulates until sea level rises. All that swamp, all that vegetation covered with coastal sediment when the sea level rises. All those strata, all those different environments preserved in the record of cyclothems. You've got to ask, what's causing the repeated environmental changes during the Carboniferous? The answer is glaciation. North America and Europe were near the equator, but the Carboniferous had a southern supercontinent, Gondwana, in high latitudes. South Africa was at the South Pole during the Carboniferous. As the Gondwana glaciers grew, sea level dropped and rivers, lakes, and swamps covered shores of inland basins that formed in North America. When glaciation ended, the water in the ice sheet goes back into the ocean and sea level rises. Each cyclothem represents climatic change. Of course, even though the ice sheet is at the South Pole, the global sea level rise still affects the equator. So melting ice sheet and the submergence of coastal swamps, it has a familiar ring, doesn't it? It turns out because all that vegetation was storing atmospheric carbon and the ice sheet was cooling the southern oceans, the Carboniferous probably had similar temperatures to what we have today. One of the few times in the geologic past that has happened. During most of the geologic past, the Earth was warmer than it is today. Do you understand why sea level rise results in burial of all this coastal vegetation? In geology, it's called a transgression. When sea level rises, of course, the absolute elevation of sea level is higher. But the ramifications for the coast are drastic. When sea level rises, the shoreline moves landward. What was once beach is now underwater. It's like high tide, but on a larger and longer scale. What was once coastal forest or swamp is covered by marine sediment. The entire cyclothem package, freshwater sediments, coal seam, brackish shale, and finally marine clay, represents a transgression, a sea level rise and landward displacement of the shoreline. Do you see the sea level drop in a cyclothem? You do, and this is where geology gets interesting. The drop in sea level is represented by an erosional surface. When you drop the sea level, the land surface is exposed and it erodes. It's a break in the sedimentary record. That is until the cyclothem sedimentation starts up again. Until the rivers start forming deltas and bayous, there is no sediment. So you are still reading the rock record, even though there are no rocks. No rocks mean there was a lowering of sea level. It's called a regression. What caused it? Glaciation in South America. What was going on in North America? The land surface was exposed, as it is today when we have a glaciation of Antarctica. The exposed land surface was being eroded and weathered. It's important to note all that exists in the rock record is a contact surface between two cyclothems. It's called an unconformity. And yet you can still interpret geologic history. Coal seams and the strata that surround them represent change. Change in sediment types, change from rivers to lakes to swamps, change in sea level, all driven by climate change. It's a great rock record to read. Of course, reading the record of coal beds and cyclothems isn't possible everywhere. Is there a way you can use what you know about transgressions and regressions to do stratigraphy anywhere? There is, at least anywhere there's sedimentary rock in North America. I've mentioned that the North American tectonic plate formed billions of years ago. Once it formed, it existed as a stable platform or craton. During much of that time, strata accumulated on much of the craton. Does that mean that the stratigraphic record is the same everywhere in the US? No, but there is enough consistency that with a little bit of knowledge, you can interpret the stratigraphic record. Here's how. Let's take the Paleozoic era, 570 to 220 million years ago. Through much of that time, North America was near the equator and shallow seas covered most of it. During that time, the only thing that affected the sedimentary environment were changes in water depth. That's right, transgressions and regressions. It turns out that the rocks deposited during the 350 million years of the Paleozoic can be divided into 4 large transgressive events. Just 4. Each of those events is characterized by very similar stratigraphy. You start with dry land, then shallow water, and then deeper and deeper water. Sandstone, shale, limestone. A transgressive sequence. At the end of each transgression, there is a rapid regression and the exposure of dry land again. What causes that on a continental scale? Glaciation or tectonics? It's the same principle we discussed with changing sediments associated with coal beds, just bigger scale. Here's a diagram of the transgressions in North America. 4 in the Paleozoic, which are recorded throughout the U.S., and 2 in the Mesozoic, which are mostly recognized in the West. So as you're looking at strata, ask yourself, are you seeing sandstone, the beginning of a transgression? Shale, a time of rising sea level? Or limestone, a deeper water environment? If you are in the Midwest or the East, you have a good idea of where you are, not only in terms of the transgressive sequence, but also the age of the rocks. The 4 transgressions begin in either the late Precambrian, the mid-Ordovician, the early Devonian, or the late Mississippian. Of course, as we saw with the coal stratigraphy, minor fluctuations in sea level are superimposed on the large ones. But that makes the detailed descriptions more interesting. You can interpret a lot with stratigraphy. Let's try some interpretation of geologic history using your knowledge of stratigraphy in combination with what we learned about in our early lecture about landforms. Here's a photo of the Toroweap-Tuweap overlook within Grand Canyon National Park. From what you know, I think you can do a pretty good job interpreting the geologic history that is shown in this photo. Let's look at the landforms first. Front and center, in fact, it's the subject of the photo, is Vulcan's Throne. The Toroweap-Tuweap overlook is just to the right, the east of Vulcan's Throne. It's a volcano, no doubt about it. The reason there is no doubt about it is it's very young geologically. It's hardly been eroded at all. That's an important observation and interpretation that you have just made. What about the other stuff? Exposed along the entire right-hand side of the photo are sedimentary units. I gave that away when I told you that this is the Grand Canyon National Park. But what type of sedimentary rocks are they? You know that answer right. This is the arid southwestern U.S. Look for both slope-forming geologic units and cliff-forming geologic units. In an arid environment, what units form slopes? Shale. What units form cliffs? Limestone. Just to keep you from worrying, we have a little bit of a break in this stratigraphic record because there's so much sandstone. Sandstone can appear differently depending on the characteristics of the rock. So let's go through it, starting at the top. On the horizon of the right-hand side of the photo is a resistant cliff-forming unit that holds up the plateau, limestone. Underlying that limestone unit is a slope and then another cliff. That would be a thin shale layer and another limestone unit. Below that are broad sweeping slopes that have formed on a thick shale unit and bring you down to the floor of the Toroweap Valley, the valley that extends back to the horizon in the center of the photo. The Toroweap Valley is underlain by a sandstone, a mixed bag of resistant and non-resistant units that you can see just to the right of the base of Vulcan's Throne. So you have it, right? Dropping down into the canyon itself, things get a little clearer. The sunlight is shining on this beautiful sequence of limestone cliff formers. Below those, in the bottom right corner of the photo, is a hard-to-see shale. So just looking at the geomorphology, you can identify the limestone cliff formers and the shale slope formers. That lets you interpret the history of the sedimentary sequences. Shale is near-shore sediment, and the limestone is deeper water. Limestone is deposited too far from land to receive clastic sediment. Each time you transition from shale to limestone, you record a transgression, rising sea level. You don't know the names and ages of the unit just by looking at the photo, but you do know the geology, and you'd be able to interpret the geologic history. But I will tell you, the uppermost units in the photo is the late Permian sequence with Kaibab limestone on the top, the Toroweap limestone making up the next cliff down, and then the slopes that are made up of the Hermit Shale. The Supai Group, a mix of sedimentary rocks, occupies the valley flat. The cliff below Vulcan's Throne is capped by the beautiful Mississippian-aged Redwall limestone, and in turn, that is underlain by early Paleozoic deepwater units, the Temple Butte limestone and the Mauve limestone. At the very base of this section is the Bright Angel Shale. The geology you're looking at represents the last 3 of the 4 Paleozoic transgressions. But you're not done. There's a lot more geologic history to interpret. Look at Vulcan's Throne. Beneath the throne are rocks that are different from the Redwall limestone. The Redwall is pink. The rocks below the cinder cone are black. Those black rocks are volcanic units as well. But how did they get there? Side by side with much older Redwall. How do you get side-by-side contact of different age rocks? One easy answer is a fault. Look at the Paleozoic units on either side of Vulcan's Throne. The Redwall limestone is exposed immediately below and to the right of Vulcan's Throne. How about below and to the left of the throne? The Redwall isn't there. Instead, there's the weak cliff-forming units of the Supai Group. The left side of the photo is dropped down relative to the right side. You can also see, if you try to match up the Kaibab limestone at the top of the sequence, the right side of the horizon doesn't have a match at the same elevation on the left of the photo. There is a fault there. It turns out the fault created a zone of weakness, which enabled rivers to downcut and create the ancient Toroweap Valley. Those volcanic units up against the Redwall limestone were a series of volcanic events that filled in that valley and dammed up the Grand Canyon. Vulcan's Throne is the most recent of these volcanic events. And if you look at the center of Vulcan's Throne, you can see that the fault is still active and has recently cut the cinder cone in 2. So other than the ages of the units and faulting, you understood the geology, right? You identified the rock types, you interpreted the sequence of events, you reconstructed environments, and you figured out the tectonic history. Congratulations, you're getting good at this. As a relationship between strata and time grew clearer, geology came into its own as a science. James Hutton, who is frequently called the father of modern geology, realized the importance of both strata and the absence of strata, called unconformities. When regressions occur, time is passing, and geologic processes are still occurring. It's just that the only record of a regression is an erosional surface. Right now, sediment on North American continent is being eroded away. All the sediment that the glaciers deposited during the last ice age will eventually be eroded. This is the harsh reality for a glacial geologist like me. The glacial sediments that I've spent my life studying will probably not be preserved in the geologic record. So it turns out that as immense as the stratigraphic record is, it only represents a small portion of geologic time. There is more geologic time represented by the gaps in the stratigraphic record than there is in the rocks of the stratigraphic record. And Hutton recognized that. Hutton used to go to an outcrop near his home in Scotland called Siccar Point. It overlooked the ocean. The outcrop exposes sedimentary units that are 425 million years old, standing almost straight up and down. Those strata are covered by sedimentary rocks that are 345 million years old that are at a different angle than the sedimentary rock below. They are separated by an unconformity. Of course, Hutton didn't know plate tectonics, but he did know that the unconformity involved the deformation of sedimentary strata. So he read the rocks at Siccar Point. You can do it too. Look at the picture. The vertical rocks at the base of the outcrop were sandstones and shales that had formed in an ocean 425 million years ago. What happened to them? Those rocks have been deformed until they stood almost straight up and down. Tectonics. Then they were eroded. The unconformity formed, and another ocean began accumulating sediments on the same spot 325 million years ago. That's when the upper layers of the sediments were deposited. But those originally horizontal strata were deformed during the tectonic events that made Scotland. But here's the important part. Look beyond Siccar Point. There's an ocean now, and in that ocean, sediments are being deposited and strata are forming. And one can hazard a guess that these newly forming strata will one day be deformed. Hutton wrote, "The result, therefore, of our present inquiry is that we find no vestige of a beginning and no prospect of an end." After Hutton, geologists were no longer constrained by the idea that the world was young. Geologic processes could be imagined over millions and millions of years. Hutton is considered the father of modern geology because he opened up a whole new way of looking at the planet. Hutton gave the world deep time. Hutton told the world that there would always be sediments forming. There would always be mountains rising, and there would always be erosion, making things flat again. So now you know how to read the rocks and tell their stories. And I encourage you to open the book and read as you run.